So we've got we'll start off this morning with a bit of review. We can't forget about chapter 5 number conversions, because next week we'll be doing IP addressing, so we'll need to do these conversions again. So let's do a little bit of review before we go into chapters 8 and 9 under today's chapters. So let's start off with converting across 112. Let's see if I put that correctly in. Yep, got that right in Discord. For those that are on the Discord and be watching this later. So the first thing we do, 112, work out where it fits in over here. So it'll be 64. So 12 minus 64, 8 carry the 1. This is 48. If my maths is correct, which is a 32 and a 16 and then zeros. So this will give us 1, 1, 1. Four zeros. Nobody disagreeing with that? You're all so chatty this morning. Okay. So the next one, converting it to hex, we separate it into our 2 4-bit sections. So we take this one first, which is 421. Which is 7. And that one's 0. So it's 7, 0. Okay. Let you digest that a little bit while I feed this across to You're all in shock that we're having to do maths this early in the morning? No? Everybody's quiet. I think this is scary. Alright, 74. So again, let me just take that out of the way. So, get back there. We will have a 64 with 10 over. Get rid of that. So 74 minus 64 is 10. So 32 doesn't fit in there, 16 doesn't, 8 does with 2 remainder. This is now 1, 0, 0, 1, 0, 1, 0. Break that into our groups of 4 binary digits to give us our hex. And when we do the hex, it's 421. So the first number is 4, and we have an 8 and a 2, which gives us a 10. 10 is equivalent to A, which is 4A. So the next one, we've got 28, so we have a 16, which leaves us 12, which is an 8 and a 4. So 11100. So that gives us 1, an 8 and a 4 is 12. So we have A, and 12 is C. Yes, Cooper, it will be a double chapter. Alright, so I'll post up a worksheet for conversions into Discord this morning, so people can work their way through that. It's not big. There's like 30 slides in the chapter 8, and I think there's 16 or something in chapter 9. So no, it's nothing like chapter 11 from IT Essentials. No, that was just horrendous. That's why I split it up into 4 groups of videos. So, alright, so that was just a quick refresh of doing the conversions. We will, as I said, post up the worksheet, and we'll look at network layer today for the first one, and then take a break and come back for module 9, which isn't that big. All right. Yeah, unlike IT Essentials, Windows configuration chapter, that was huge. So today we'll have a look at what the network layer does, explain how the headers of IPv4 and v6 packets are used, how they generate routing tables, and how decisions are made using those routes. Alright, so the network layer is layer 3 of the OSI model, and this is where logical addressing takes place, and the 2 logical addressing protocols we'll be looking at is IP version 4 and version 6, and we'll look at the basic operations of addressing the end devices using those two protocols, how the encapsulation works. Remember, when it comes down from transport layer into network, it becomes an IP packet after it gets encapsulated with the headers for this layer. We'll look at how routing works and then de-encapsulation at the final destination. So when the segment is passed down from the transport layer into the network layer, it becomes a packet after it's encapsulated with the IP header. And the basic information in the IP header is the source and destination IP address. Okay, and just as a side note, network address translations do not modify the original header information. They actually add another layer of encapsulation, if you like. So IP is meant to be low overhead and it is connectionless because it doesn't basically do error detection and correction and that sort of stuff. It just transports the data it has. So it's known as a best effort protocol, and it relies on upper layers to do that error detection and correction, such as TCP. It's media independent. In other words, it doesn't care whether it travels across copper, fiber, wireless. It really makes no difference to the IP packet. So what does connectionless mean? It means it doesn't connect with the destination before it starts sending the data across to that destination. It's equivalent to the old snail mail. So you would just address your envelope, which is what IP does. It puts a destination address on it and a source address on the back of the envelope, and you drop it into the mailbox for delivery. All right, so same with IP. It puts that source and destination address on and puts it on the wire for delivery. It doesn't care whether it gets to the other end or not. It just sends it. So if it was connection orientated, you would have feedback from the other end before it would actually send information. And we'll look at that when we look at TCP in more depth. So IP is best effort because it doesn't guarantee delivery of the packets to the destination. It doesn't have large overheads because there's no extra mechanisms in the protocol to check and resend information, so it doesn't contain a lot of information in the header, and it will just send the packets out as they get them and hope that it arrives at the other end. So what do we mean by media independent? As I said earlier, we are talking about the fact that you can transport it across any media type. So we don't need to change the IP packet based on whether it's copper, fiber, or wireless, or serial links, or over a VPN, or whatever we're sending it over, because that is the requirement of the, what was it last week? Frames. Remember when we were talking about frames? It had all these sub protocols that actually handled your media access control. So that's where the actual media is addressed in layer 2. So this is layer 3, so it doesn't care about what media it actually goes across, because it relies on layer 2 doing its job in adding the appropriate information for the media itself. Alright, so IP is unreliable in that it does not retransmit for errors, it doesn't realign packets to make sure they're back in order. All of those things must be done in layer 4, transport layer. So we do have a maximum transmission unit for IP, and it's basically 1500 bytes as a rule of thumb. And what that means is that's how much data it can take. Okay, so what happens if we have something that's above the maximum transmission size? We break it up in smaller parts. So we fragment it, breaking it up into smaller parts so that it's within the MTU is known as fragmentation. Now, this causes some delay. Delay is known as latency in a network. Now, please note that IPv6 does not fragment packets. Okay, so it'll just send the larger size. So IPv4 headers, we are looking at the header to get the destination IP address out of it. Within that, it contains some other fields like time to live and things like that. We'll look at that in the next couple of slides when we actually look at the header. But you'll also notice that when we're looking at it, there's no space there for error detection, resends, and that when we look at the actual headers. So when we look at it, we're looking at approximately 20 bytes of information added to the data that we're transporting. And the main things we need to take from this is, when we look at it, each of these rows is 4 bytes wide, i.e. 32 bits. Okay, we have the version of the addressing, so v4, v6. The v6 header looks different because we're dealing with 128-bit addresses, so the headers have changed. So the version tells it what version of protocol it's dealing with. We have, in this section here, we have our quality of service markers, and the other ones we really need to check is the time to live, confirmation of the protocol that is being transported. So in other words, whether it's transporting for TCP, UDP, it lists it there. And then our source and destination addresses. The other bits and pieces in here, like the header checks, fragment total lengths, we can do, when we fragment and do extra things, we can tell it to do some extra things, which generally speaking is not used in networking, but we can extend the length and tell it to combine things together to give it extra capability. Most of that functionality wasn't adopted in mainstream IPv4 use, but it's still, those capabilities are in it. So this is why we only concentrate on the version, quality of service markers, time to live field, the protocol. source and destination addresses, because they're the main ones that are always used. The others are kind of optional, and if they're not being used, they're padded out to can give you 20 bytes of header. So bitfield 0100, strangely enough, equals 4, doesn't it, in binary? Then, as I said, we've got the quality of service section, header checksum to make sure that the header is intact and all correct. Now, time to live is the hop count. Every packet has a maximum lifespan on a network. If it stays on the network too long, it's discarded, because it basically assumes that it's formed a loop and it cannot be delivered to its destination. The protocols are, as I said, the protocols from the next layer. So what protocols is IP transporting? So what TCP, UDP, so what layer 4 protocols it is carrying, so that when it de-encapsulates this information, it can pass it up to the correct part of layer 4 at the destination. Then our source and destination addresses, once again in 32-bit notation, so zeros, ones. There are limitations in IPv4. If we didn't have limitations in IPv4, we wouldn't have needed to go to IPv6. So basically, what was the limitations? Lack of address space. We basically ran out of IPv4 addressing, because the way it was originally designed was wasteful. We'll look at this in depth in chapter 11, when we do IP addressing, specifically IPv4 addressing. And the history of it is everything had to be divided in equal sizes. So if you had a segment of network that needed 30 addresses, then everything needed to be cut up in chunks to cater for that 30 addresses. Even if you, like on a point-to-point link, you only need 2 usable addresses, you would have to assign that point-to-point link 30 addresses so that it would be the same size as every other chunk of space in the network. So it was very inefficient in the way it assigned addresses, and that ran into a depletion of address spaces. How we patched it was we introduced CIDR notation, which is classless inter-domain routing, which we'll look at when we do routing in depth in the next unit, when we do routing and switching in big detail. But just be aware that what we did was basically patch the protocol, and we allowed network address translation, which you're all familiar with, is where we use one live public address, and then we have all these private address spaces in behind. So like you have on your home router, you have one IP address which is assigned by your service provider, and then you have all of your devices working behind that router using network address translations. So they're converting all of those addresses to one common address that is seen by the outside world. IPv6 doesn't allow for this network address translation process that we're used to. So we basically have live addresses throughout. So not to worry. It's going to be fairly easy to set up. The main difference is one uses the dotted decimal notation, i.e. the 32 binary digits, and the other one is 128 binary digits represented in hexadecimal format. So we'll worry about that when we get to chapter 12. But if you look at the address spaces, you come down here and, we have 4 billion IPv4 addresses in the world and 340 unidecimal, or how, decimal? IPv6 addresses. So, okay, we have 4 10 to the power of 9 against 340 10 to the power of 36s, which is quite a substantial change in the number of addresses we have. It's been coined saying we can put an IP address on every grain of sand in the world and still have stuff left over, to give you the kind of idea of how many addresses we have. We've got lots left over. So the IPv6 header is very much just the core information that we need. So we have the version, the traffic class is our quality of service, source and destination IP addresses here, hop limit, which is our time to live equivalent, flow label, payload length, next header. So we can actually stack headers and increase functionality and do some funky stuff that is unique to IPv6. So if we were having different functions put in, we could put another, encapsulate in another header, and this field tells it that there's another header to go read to get extra information from. So strangely enough, the version will be 0110, version 6. Traffic class is equivalent to our quality of service field, 1-for-1. Flow label is different, payload length is different, so this one's just indicating the length of the data that we are encapsulating. And basically we have much larger address spaces because we're dealing with 128 bits of IP address for source and destination. So the actual header itself is larger, but the number of fields that we use inside the header is reduced. So it's more efficient and easier to use because we don't have as many fields within it. Okay, so here we, as I said, we can extend the headers, we can re-encapsulate a header within a header and provide additional optional functionality by using extra headers. There's basically, why would you do it? If you're encapsulating it for security, you don't want to fragment it, so you break it up into different headers to cater for it. And there's certain protocols out there that basically strip headers and then look at the headers to make quick forwarding decisions. There's all sorts of different ways route forwarding works depending on the protocols being used. Forwarding decisions are based on the network address. Now, again, every device needs a forwarding table in it, including the host machines and our routers and switches. Now, depending on what type of device it is, depends on how it makes its forwarding decisions. We talked about switches using the MAC address and using a forwarding table based on the layer 2 addresses. So hosts will make the same sort of table, but based on the IP addresses of the network that it wants to connect to. So we have local hosts that are part of the same network, and then remote hosts which are available via another forwarding device, so our gateway. So anything on the other side of the gateway is known as a remote host. Anything that is within the same network segment, i.e. this left-hand side of our gateway, that would be known as the local hosts. So what does it use to make these forwarding decisions? It uses a combination of the IP address and the subnet mask. The subnet mask is used to strip away the individual host address and leave it with just the network address. And each routing table or forwarding table is based on how do I connect to a network. Okay, that's from a router's perspective. From an individual host, you will have the source address, well, it would be the destination address for the forwarding decision, and it will do an address resolution against that address, which is basically saying what MAC address do I forward this to make it go towards its IP address. Now, if you remember in the framing, the MAC addresses are only used in a per hop to get it from one device to the next, and we need to have a pair that matches the layer 3 address to a layer 2 address to move it forward. And you're probably going, I don't remember any of this. This was all so last week. We've had lots of other things in between there. That's all right. It will come back to you as we do the labs. There are a few packet tracer activities to do during this chapter that explain the forwarding decisions and look at it as we go through. So just bear with me as we go through this. Default gateways, as I've said before, is the way off your local network and into the greater world. It must have an IP address that is part of the same network because it is the exit, so it is part of that network. And it accepts all traffic from that network that wants to get outside to remote networks, and every device should have a default gateway configured so that it can send it to that gateway and forward it on. So basically in that last line there, no default gateway means it can't leave the network because it doesn't know where to forward the traffic to. So host routes. We will have a look of the host table and have a look at what is actually in there. But basically we need to have a entry. Remember when we went through setting up each individual host in the material we've done so far, we gave our PC its address, so 192.168.10.10, and we would have a subnet mask of 255.255.255.0, and then we would have a default gateway underneath it of 192.168.10.1. So basically we say this is my address, and to get off this network we've got to go to this device to get to anything out here in the remote world. If it's just traffic bouncing between PC1 and PC2, it'll do what's called an address resolution using ARP, which says I need to get to 15, and PC2 will reply saying this is my MAC address, and then it'll just forward it directly to PC2. If it's for any other address that is part of the remote, when it does an address resolution, because it's got a default gateway, it sends a request for address resolution again, and router 1 will reply with its MAC address, and anything for that remote address will be sent using routers 1 MAC address as the destination at layer 2. So it will go out into this world via the gateway. I hope that jogs the memory from the previous chapters we talked about. So how do we have a look at what our individual host routing table is and what interface and the cost and all that sort of stuff? Well, we use netstat-r, and a default route, i.e. where our default gateway would be. So if we don't have a specific entry, this will always match. Here's our gateway. How do I get there? I send it via my address. So if we come back here, if I where's me that's the one I want. Alright, so this is our PC1 looking at .10. Alright, so when we're leaving host 1, it's 192.168.10.10. So this is the local address or the interface that I send the information via to get to this gateway for any route that I do not know. That's called a default route. Alright. Basically the way routing tables work is it does a search along these addresses, there's the address. It's this network, that mask, so it's the 192.168.10.0 network. I send it out of this interface. And you're going, well, wouldn't it all be that interface? Well, technically it is, because the 127.0.0.1 is the same as that one. It's your network card. Okay. So if we pull up my command window and do netstat R, and okay, so there's all the interface lists there, all the various MAC addresses, and you'll notice here that I have a default gateway to my router. This is my IP address today, 143 inside my network, and these are all the known addresses that I'm sending information to, and these are the interface addresses that I send it via to get there, and the metric is the cost that it will, the waiting. So when I can get there via the same address, right, if it's the same, if I've got multiple paths to the same destination, I look at the metric and see which one is going to cost me the lowest amount, and that's the one I would use to make the forwarding decision based on. Okay. We're almost finished the first section, so it's almost cover time. Forwarding decisions. So the way it works, I'll just hopefully make it a little bit clearer in this one. So we are sending a packet of information via from our PC1 to our PC2. So we want to connect to this device over here. So to get there, we need to have a host forwarding table that says to forward it to my gateway. Then in router 1, it'll pick it up and look at the IP header and look at the destination network. And the destination network says I need to get to 10.1.2/0. And you're going, okay, so how do I get there? I get there via router 2. And there's a typo in this diagram. Alright, that should be 110/24. That would line up with the routing table and what's on these envelopes over here. Alright, so back. Okay, so this address there is wrong. That's actually 10.1.1.0/24. That makes better sense. Alright, so what happens is router 2 basic format is router 2 knows every network that is directly connected to it, and it will share its information with router 1. Router 1 knows these two networks are directly connected to it and shares that information with router 2. And that way they build up total knowledge of the networks that it can get to. So when we look at the routing table in router 1, it knows about the 192.168.0 because it's directly connected via 000. Then we've got the 209 network that links it to router 2 via interface G001. And because router 2 shared this network connection with router 1, router 1 knows it can get to 10.110 via router 2. So what it will do is it will send any traffic for 10.110 out of this interface to router 2 so that router 2 can then forward it on to this network and ultimately to PC2. The types of entries within the routing table are directly connected. Okay, so any cable connecting to a router is considered a directly connected route. Anything it learns from another device is known as a remote route, and these can be manually configured or learnt dynamically from routing table sharing, and we'll look at that later on. And the last one there, default route, is where, just like on the host, the default gateway or default route is known as, if we don't have a specific entry within our routing table, we'll send all of the traffic via that default route, and hopefully another device will know what to do with it as it travels through. So what do we need to configure when we want to configure a route? So a static route is one that we manually configure on our devices, and we need to give it some basic information. That basic information is, I'm going to configure an IP route. This is the network address, this is the subnet mask, and this is where I send it to get it towards the final destination. So this is known as the next hop address. So when we look at it on the topology diagram, to get to the 10.110 network on router 1, I need to send it to router 2, which is my next hop. What is the closest IP address of router 2 for me to send it to? That's the next hop address. Okay, so the next hop address here is 209.165.200.226, because this is the interface that I need to send any traffic for this network to router 2 on, for it to know what to do with it. Now, the problem with static addresses is if something happens, okay, in this example here, we have router 3 hanging off down here, giving an alternative path, and if this link fails and we have a static route, the traffic won't go via this change. It'll just go, oh, this static route is no longer valid, and remove it from the routing table. it will not reroute via another path. Okay. We would have to manually come in and make the change saying to get to the 10 network, we now have to go via router 3. So we would have to redo this again, but point it to the router 3 interface, and then have the same thing configured on router 3 to come up here, and vice versa, coming back down this way. So the problems with static routes is that every time a topology change occurs, we have to manually go in there and create new entries every time something changes. They do not respond well to changes in the topology. They do not learn, but they are very good on small networks. Like in this example here, there's only one path, so having a static route is perfectly acceptable. Where we've got multiple routes, it gets a bit more complicated. Dynamic routes is much better than static routes in that it will learn and share information between the routers. They share their routing tables with each other, and when something changes, like in our second scenario there where our preferred route disconnects for some reason, it's no longer available, it quickly goes, oh, I've got an alternative route here, this is now how I can get there, and it will update its routing table. How do I confirm what is in a routing table? By typing in the show IP route command in the device, and you're going, but how do we connect to devices? We haven't really covered that. Well, we've got Packet Tracer, and I'll go through it again with you. Okay, so we have a code here that tells us what all these letters on the side represent, and so they're available. So the S is a static route, the O, if we look it up, will be an OSPF route, the L is a local route. So you'll start to learn these as we work our ways through them, and when you're looking at live equipment, it always displays this little codec explanation of what's going on as part of the display, so it's always there. So in this chapter we learnt the basics of how forwarding works on a host machine and a router. There are a couple of videos within this chapter for you to look at to hopefully make those explanations clearer than what I made them today, because my brain is still not 100% from yesterday's cold. But what I want to do is bring up, before we take the break, well, 10, so we've only been going half an hour. Alright, so I'm going to quickly bring up Packet Tracer, which is firing up in the background. I'll just log into it. When you log in to packet tracer, use your Cisco Netacad login. And what this does is it provides the full functionality of packet tracer. If you use the guest login, it doesn't provide you with full functionality. Okay. What I'll do is I'll make a separate video on how to use packet tracer. But the basics is down the bottom here we have routers and switches. Now within the Netacad course, we'll have, once I log into it again, 101 login screens. And we wanted to go into that one. So when we go into the modules, so when we look at the course, yes, I want to go into the course, thank you. And we come down to network layer. Okay, so these are, strangely enough, just like all the slides that we just went through. Alright, but if you come up into the course index, we'll have packet tracer activities. So if we just general these off, come down to oh, it doesn't have any for 8. I thought it did. Alright. That's a lab. Alright, so when we get chapter 9, you just need to click on the packet tracer activity, and then you can click on the download for the activity, which will be a packet tracer PKA, which is a packet tracer activity file. Save it down, and then when you open it in packet tracer, it'll load up. Okay, so this will give you your scenario, and this is your instructions for use within the scenario. Step by step, so just read the instructions and it'll tell you what to do step by step. It's got the pre-built lab in it, and you just got to follow the instructions step by step to go through the activities, and you can use the check results and reset activity buttons. Check your results to see how far through it you've progressed, how much of it you've done correctly. And reset activity is remove everything that you've done, reset it back to its original condition so that you can learn. Now, as we go through, more and more we'll build up to using this more often. Packet Tracer is great for you at home. It allows you to work at home with equivalent to equipment. So basically this is a router and switch and host simulator. So a full network simulation software package that you can download and use as part of the Netacad course, which I'm hoping I've gone through with you before, but my brain's not with me 100% today, so I'm just hoping I've done this with you before, and not just with the other group. I'm hoping I've done it with you as well. So if I come back to this page, okay, Cooper, good. You've been, so I've talked about Packet Tracer with you guys before. This is good. All right, cool. So yeah, for each chapter that it has activities, it comes up in the page and the link there. Just download them off the site and it'll open it up in Packet Tracer and just follow the step-by-step instructions. I will, as we start moving forward, start introducing ad hoc exercises for you to do. So I'll just draw a topology and say, go make this in Packet Tracer. And you basically join the devices together, build the network, and configure the devices so that you can, test your ping between like PC1 and PC2, like in that last. Okay, if you wanted to, you could build this up. Okay, there's nothing wrong. All right, you know how to do an IP route command there, so you could put static routes in and build it up and build this topology and actually build it so that you can ping from PC1 to PC2. All right, using Packet Tracer as a bit of a learning self-exercise for you to do. Now, I'm going to end the recording here. Enough of my rambling.